So we talked about the various processes that I can take my ideal gas through. What happens when we go around an entire cycle? So let's say we're going to start in state A, and our system goes from A to B, then B to C, then C to D, then D back to A. So we have a complete cycle as we go all the way around from state A back to state A again. Well, what do we know about our system as it goes through this complete cycle? Well, the first thing we can say is we know that the change in the energy over the complete cycle has to be zero, because energy is a state variable. If we start at state A and we end up back at state A, then the energy has to be the same. But if our final energy has to be the same as our initial energy, which means the change in energy has to be zero. We also know that the work done by our system is going to be positive over this cycle. So as I go from A to B, I have a larger positive area under the curve than when I come back from C to D. So my smaller negative area plus my larger positive area, and again I've got no area of the curve going from B to C and no area of the curve going from D to A. So I know that my net area under the curve here is going to be positive, which tells me that the work done by my system is going to be positive. So, and this is true for any time that I go around a cycle in a clockwise manner. So if I'm going clockwise around my cycle, that means that I have to have an expansion that has a larger area under the curve than my compression does as I come back. Now, from the first law of thermodynamics, if the change in the energy is zero, that means that the net transfer of energy into and out of my system as heat has got to be equal to the work by. So my net Q for the entire cycle also has to be positive, which tells me that in terms of their magnitude, so I know that Qn will be positive and Q out will be negative, but ignoring the signs and just thinking about the magnitude, that tells me that my system is going to take in more energy as heat than it will dump out. And sure enough, there happens to be a very particular relationship. It tells me that the energy that my system takes in as heat, basically it's going to turn that into two things. So it's going to take in all that energy. Some of it is going to be converted into the work done by the system, and then the rest is going to be dumped out as an exhaust heat. So this is what defines an engine. So as I go around my cycle clockwise, basically I have a positive work done by the system that comes from taking in an excess, taking in a large amount of energy as heat, converting some of that into work, and dumping the rest of it out as exhaust. So this is fundamentally what an engine is. So our schematic that's sort of showing this is, again, we have some hot reservoir that, again, is going to allow us to transfer energy as heat. So up here, the energy is at a high temperature, right? The system's at a high temperature, so I can transfer energy in as heat. And then that energy that gets transferred in is going to get converted. Some of it's going to get converted to go do work. The rest is going to get dumped out to some cold reservoir. And again, this is what we talk about when we talk about an exhaust. Now, clearly, the more of this energy that I can convert into work, the more efficient this engine is going to be. So we can calculate the efficiency of an engine with this expression. So our efficiency is going to be given by, well, it's the ratio of the work done by our system to the total amount of energy that we had to transfer in as heat. So the more of that energy we transfer in that we can immediately convert into work, the greater our efficiency is going to be. So if I just rearrange my equation here and solve this for the work done by, I'll see that the work done by is equal to Qn minus the absolute value of Q out. And I can plug that in, and so I can rewrite this expression to calculate the efficiency as 1 minus the absolute value of the energy that I dump out of my system as heat, divided by the energy that my system took in as heat initially. And so I I can calculate the efficiency of my engine by knowing sort of any two of these three things, right? So I can figure out the QN or the work by, or I can do it with QN and Q out. Now, if we think about the system we were describing initially, again, as we went through our cycle, as we go from A to B, it's an isobaric expansion. We know that we're going to go to a higher temperature, so our energy is going to increase. We have positive area under our curve for the expansion, so we know we're going to have positive work done by the system. And again, our first law tells us that this plus this has got to be equal to the energy transferred into the system as heat. So I know that I will be taking in energy as heat along that step AB. On my process BC, well, I know I'm dropping to a colder isotherm. And because this is an isochoric process, or a process at constant volume, there's no work done by the system. So again, something negative plus 0 has to give me something negative. So I'm going to be losing energy as heat along the step BC. CD in this particular example, well, this is an isobaric compression. So again, I'm going to go to a colder isotherm. So my energy change will be negative. I have a negative energy under the curve as I have a compression. So my work done by term will be negative. And so two negative things added together is going to give me something negative in terms of the energy transferred out of my system as heat. From D to A, so this should read D, but from D to A, what I'm going to have is, well, I'm going to a hotter isotherm, so my energy will increase. Again, because it's a constant volume process, there's no work done by the system, which means that from D to A, my system has to take in energy as heat. And so what that tells me is, for this particular cycle, Qn is basically adding up the energy taken in as heat along these two steps. So from D to A and from A to B. Q out, on the other hand, happens to be calculating the energy transferred out of my system as heat along these two steps, BC and CD. And so then the work done by the system is the area inside this box. And so knowing those three things, Q in, Q out, and the work done by the system, again, I can go ahead and calculate the efficiency of my engine. So in this case, if I do work by and Q in, I could do it that way. If I knew Q out and Q in, I could use the second equation here to calculate the efficiency. So it's just important to recognize that for this particular process, I happen to have two states each where my system is taking in energy as heat, and then two more states where it's getting rid of energy as heat. So let's go back to the beginning. And this time, let's turn our cycle around. So instead of going A to B to C to D back to A, let's go A to D to C to B back to A. And so what you'll notice is instead of going clockwise around our cycle, we've gone counterclockwise. And so this time, what I've got is again, the energy change is still going to be 0 over the complete cycle because I'm back where I started. This time the work done by my system is going to be negative. So I have a larger area under the curve for this compression than I have positive area under the curve for this expansion. So then work done by my system is going to be negative, which means that the work done on my system has to be positive. So to get my system to go through this cycle, I have to do more work on the system than what the system is going to do on its external surroundings. Last but not least, again, from the first law, I know that the net energy transferred into or out of my system as heat through this cycle has got to be equal to the work done by my system over this entire cycle. So that also must be negative, which tells me in this case what I'm actually doing is I'm dumping out more energy as heat than what I take in. And so again, there's a relationship that defines how this happens. And so for this particular cycle, what happens is my system takes in some amount of energy as heat, and then I do work on that system. It combines these two terms and dumps all that back out. So this is it takes in some energy as heat, I do work on the system, and then the sum of those two things gets dumped back out as heat in this Q out term. This is what defines a refrigerator. So one way to think about a refrigerator is that it's simply an engine running in reverse. So instead of with an engine, it takes in heat and converts that into work and exhaust. A refrigerator does just the opposite. So it's going to take in some energy as heat. You're going to do work on it, and it's going to dump out all of that as an exhaust. And so here's our schematic for thinking about what's going on with our refrigerator. So again, notice for my refrigerator, what I take in, the energy I take in as heat, is actually coming from the cold reservoir. Right? That's your refrigerator literally is trying to take energy that's inside it, and it wants to get rid of that energy. You do work on it, that's why you have to plug your refrigerator in, and then it combines those two things and dumps them out into the hot reservoir. The hot reservoir, in the case of your refrigerator, is simply your kitchen. So the kitchen is at a much higher temperature than what the inside of the refrigerator is. So your kitchen is the hot reservoir, your refrigerator is the cold reservoir. And so in this cycle, it's simply taking energy as heat out of the refrigerator as you do work on it and dumping it out as exhaust in the kitchen. That's how things stay cold within the refrigerator. So the equivalent, or sort of the analog for efficiency with a refrigerator is talking about the coefficient of performance. And the coefficient of performance for a refrigerator is again given by this ratio of how much energy do I take in, the ratio of that to the amount of work that I have to do on the system. And so again, we can rearrange this in terms of the fact that the work on has to be equal to Q out minus Q in, so I can plug that in on the bottom, which gives me this expression just in terms of Q's that really only cares about this ratio of the energy dumped out as exhaust to the energy that I took in initially, trying to cool down whatever was in the fridge. So fundamentally, an engine and a refrigerator are very similar. It's simply the direction you choose to run the cycle. So whether you have to do work on the system to get it to go around that cycle, or the system will go around that cycle and as it takes in heat, and you'll get work out, so work done by the system for an engine.